So I've tried on several occasions to convince you how important differential equations are and how to solve them. So we're going to take our last day and go over differential equations again. Now, I already did a whole video on the easiest type of differential equations to solve. When you have dy dx, the rate of change of the dependent variable with respect to the independent variable, if it's all in terms of the independent variable x, then all you have to do is take antiderivatives and plug in the initial condition to find out what c is. Now the second easiest type, and I've already done 2 of them this year, is the separable differential equations, where you have like dy dx in terms of both x and y. So it's not the easiest type, but we can separate the variables. That means gets all the dependent variable on one side and the independent variable on the other. And I usually choose to get the dependent variable over on the left side because that's what you're solving for. So algebraically, how can I do this? Well, you already have dy on this side. So if I want to bring this y to the other side, I multiply. And the same thing on this side. I have 2x there to bring there, I multiply. Basically all you're doing in this case is cross multiplying. Once you've separated the variables, your next step is always to take the antiderivative of both sides. Well, this is y squared over 2 plus a constant, and this side is going to be x squared plus a constant. Now, I've gone over this a couple times, but it's a little bit weird thing that you're doing, so I want you to understand why you can really do this. This constant can stand for anything. This one can. There's no reason algebraically why I can't combine these over and just make it a different constant over here. So now we don't have the constant on this side. And like if this one happened to be 1 and the other one happened to be 2, we could always make this, well, just -1 to put those two things, +1 to put those two things together algebraically. So I hope you understand why you can just combine those. Now we have to solve for y. So we multiply both sides by 2. And here again, when we multiply that by 2, it becomes 2c. But there's no reason why we just can't call it c. Because if this c had really been 5, then 2c would be 10. And we can let this represent any constant. So I think we're just fine doing that. I hope you understand it also. Now, when you solve for y squared equals something, y is going to be plus or minus the square root of that. Well, it can't be both. It's going to determine what your initial condition is as to which one of these two it is. Because that wouldn't be a function. That would be 2 different functions. So I look and see what my initial condition is. So we're looking for the particular solution to this differential equation that passes through the point 1, -3. This is how often they ask you to solve a differential equation like this. So what I'm going to do is put -3 in for y and put in 1 for x, and from here I can find out 2 different things. 1, because that's -3, we're going to use the negative, not the positive. And the square root of 9 is equal to 3, so c must equal 7. So that means we can write y equals minus the square root of 2x squared plus 7. And that would be the solution that we're looking for. If we had a different initial condition where that was a positive number, we would have gotten a different solution. And we've seen before that solutions can look differently at different parts on the graph to a differential equation. Okay, so let's try another one. Again, we have both x's and y's over here, so it's not the easiest type, but I think I can separate it. Again, I can just cross multiply. I can go y squared dy equals secant squared x dx. And then if I take the antiderivative of both sides, here I get y cubed over 3, and I would go plus c, but I'm going to always do the same thing I did before. I'm going to combine the c's on one side, so why even bother putting it there? The antiderivative of the secant squared is the tangent. And then I'm going to put that combined c right there. And now it comes down to solving for y. So the calculus is done, now comes the algebra. So we get y cubed equals 3 tangent of x plus 3c, but again we can call 3c just c, and now I take the cube root of that whole thing, and I've solved it, but I have to put in my initial condition that y is equal to 2 when x equals 0. Well, the tangent of 0 is 0, and we know the cube root of 8 equals 2, so c must be 8. So that means our final solution, y equals the cube root of 3 tangent x plus 8. Now this case, they didn't say to find the solution, they said to find what y of pi over 4 is. So my last step to find y of pi over 4 is to plug that into here. So I get the cube root of 3 times the tangent of pi over 4. Well, that's 1. So the answer to this is the cube root of 11. We found out what the solution was that has this differential equation, and then once we had that, we're able to plug a value into it. So now we'll go over to the other board and do 2 more differential equations, and I think that'll pretty much give you the idea. So we'll switch over to here, and just for a little variety, I put in t as the independent variable this time. Okay, again, it's not just in terms of t, so I'm going to have to try to separate the variables, and I can. So I say dy over on this side. To bring this e to the y to this side, I have to divide by e to the y. The 2t is already over here. I'm going to multiply by dt. So I've separated the variables. Now I take the antiderivatives. Now on this side, you probably are going to want to switch that to e to the negative y dy. The other side, no problem. T squared plus c would be your antiderivative. Now, what's the antiderivative of e to the minus y? It's e to the minus y, but remember we have to then divide by a negative 1. Because it's multiplied by negative 1 here, we're kind of countering the chain rule. when you take derivatives. So we're taking antiderivatives, so you have to divide by -1. And now it comes down to an algebra game again. We're trying to solve for y. This one's going to be a little more difficult, but the first thing I'm going to do is multiply by a -1. So you get minus t squared minus c. But then minus c we could just call plus c if we wanted to. Because remember, this is a general constant. And now we have to solve for y, so we have to get rid of the e. So what I'm going to do is take the natural log of both sides. Take the natural log of e to the minus y, and then that's going to equal the natural log of minus t squared plus c. The natural log of e to the negative y is just minus y, and this I just have to keep the same, and then I can now multiply both sides by a -1. So I can make that positive. I've now solved for it, but then I have to put in my initial condition that I get -1 equals minus the natural log of 0 plus c. Well, we want this to be -1. We want this part to be just 1. Well, the natural log of e is equal to 1, so c must be e. So all together, you get y equals minus the natural log of minus t squared plus e. And there is your solution. Okay, so I thought we would end things with a word problem, because that's really the purpose of having these differential equations, is to solve a situation that's really happening in the world. So, I don't know if you know about it, but Calculus Cavern is a depository for calculus homework after it's been corrected. And at the beginning of 2020, there were 700 tons of homework in the cavern. And there is a function c of t which models the amount of homework in the cavern at time t, where t equals 0 is the beginning of 2020, and it was determined that this is the differential equation that models c as its relationship is to t. We don't know c as a function of t, but we do know the rate at which c is changing with respect to t. So there is some function c and t, and that's what we're trying to find. C is measured in tons and t is measured in years. So what do we want to do? We want to use a tangent line to the graph of c of t at t equals 0 to approximate the amount of waste in the cavern at the end of 4 months from the beginning of 2020. So they're not asking us in part A to solve and find c of t. They're just saying, let's use a tangent line to approximate. So what do we need for a tangent line? We need a point and a slope. Well, the point, it's at t equals 0, so it's 0, comma, c of 0. And we know that c of 0 is 700 tons. We know that this point right here, when t is 0, c is 700, and now we need a slope. Well, that's what a differential equation gives you, is it gives you the slope. So I can say dc dt, when t equals 0, and that's why I write it like this rather than writing c prime of 0, because remember, this isn't given as a function of t. So when t equals 0, it's 1/20th, but we don't have a t, we have a c. So what do we know? They know when t is 0, c is 700. So it's actually 700 that we're going to put in there. So we get 600 divided by 20 for 30. So that's going to be the slope, positive 30. The amount of homework is going up. So, what's our equation? If you like to use y, it'd be y minus 700 equals 30 times x minus 0. Now, I personally don't like to use y and x when we're using c and t. So I would sort of say c minus 700 equal 30 times t minus 0. Or c is 30t plus 700. It's not the real equation for c of t, and that's why maybe it's not a bad idea to leave y as your variable, but that's why I put approximately, because this is just using a tangent line, not the actual graph. Somehow we've got a tangent line right there with a slope of 30 that goes through that point. So now we can say, we can use that tangent line to approximate 4 months into 2020. Well, 4 months is a third of a year, and t is measured in years. So we want to plug in 1/3. So we get 30 times a third, or 10 plus 700, or 710 tons. That's what the tangent line would approximate. Now the question is, what in B, do you think this approximation is an over or underestimate? Well, with tangent lines, what's going to determine that is whether it's concave up or concave down. If the function is concave up, it's going to go like this. Concave down, it's going to go like this. And the tangent line is either going to be an over or under approximation. So we can find that out by going to the second derivative. So this is dc dt. What's d squared c over dt squared? It's 1/20th, and then times the derivative of c minus 100. Well, it's with respect to t. So the derivative of 100 is 0, but the derivative of c is dc dt. Well, what is dc dt? It's what we already have up here. And since we know that c starts out at 700 and is increasing, we know this is positive. So since d squared c over dt squared is greater than 0, we know that the function c is concave up. So this estimation at 1/3 of a year is going to be an underestimate. So, lastly, can we actually find out what c of t really is? Can we solve this differential equation? Well, it's not just in terms of the independent variable, so I can't just take the antiderivative, but I bet I can separate the variables. I can say dc, and I divide by c minus 100, and then I've got 1/20th. I'm going to leave that over on this side, and just multiply by dt. And now I'm going to take the antiderivative of both sides. Now, this side, if you want, you could let u be c minus 100, du equals dc, 1 dc, and you'd get du over u, which is the natural log of the absolute value of u plus c, and then you put u back in and you get c minus 100. So you get the natural log of c minus 100. And I think you could see that you probably wouldn't have even had to do that u substitution if you knew that the derivative of the denominator was really just 1. But if you don't quite see that yet, just do your u substitution. On this side, you get 1/20th t plus c. And then to get rid of the natural log, I'm going to say if this equals this, then e to this number should equal e to this number. And then, since e to the x and natural log of x are inverse functions, I can just call that the absolute value of c minus 100. On this side, we've done this before, e to the a plus b is e to the a times e to the b. And e to the c is just a constant, so I can just call it c e to the 1/20th t. I'm almost there. I have to solve for c. Well, because c is 600 and getting larger, this number inside the absolute value signs is going to be positive, so I can just drop it. And now I can just add 100 to both sides. And now I can put in my initial condition that 700 equals 100 plus c e to the 0. And e to the 0 is just 1. Because at times 0 there was 700 tons. So c is equal to 600. So your final expression is 100 plus 600 e to the 1/20th t. And from that, you should be able to figure out what the real c of 1/3 is. And it comes out to be 710.084 tons. So what did we see? That tangent line really was an underestimate, but it wasn't too far off. Because you're only looking at 1/3 of a year, the tangent line did a pretty good job of estimating. So anyway, that's a pretty much a real-world type application, and I hope you can see what the advantage of tangent lines are, what the advantages of second derivatives are, and how to solve differential equations and how valuable that might be. So I think this is a good way of kind of ending up the year. And what I'm going to say as far as the year is concerned, this is ending up a Calculus AB class, which is about an equivalent to a college that would be Calculus 1 plus maybe 1/3 of Calculus 2. So I'm going to go ahead and I'm going to make videos for Calculus BC, which would include the remainder of a Calculus 2 class in a college. And that will take about half as many videos as for the Calculus AB. So thank you for listening to me, and I hope you continue on into Calculus 2.